it further.
Okay.
Good afternoon to all of you, and thank you for joining us today. I'm heartened to see that our young engineers find carbon offsetting interesting and wish to know more, because it will be a long battle against carbon emission. And you guys will be the backbone of this important and inevitable mission. That said, we want to learn from the experts. So today, let me introduce to you our speaker, Dr. Chaoming. Dr. Yu is Associate Director in Structures at Kando, Singapore. After receiving her PhD in Structural Fire Engineering from the University of Sheffield, Chaoming worked for various renowned consultants on an array of landmark projects in Saudi Arabia, Hong Kong, Macau, and Kuala Lumpur. Some local projects you may find familiar include the Sentosa Scenery Scape and the Founders Memorial in Singapore. It goes without saying that she is an advocate for the sustainable and efficient design. Today, she will provide an overview of structural engineers' responsibility in advancing net zero, the tools of embodied carbon counting, and methods of reducing embodied carbon in structural design. We will have a Q&A session after the presentation, but feel free to leave your comments or questions under the chat column at any point of discussion, and we will address them all together in the end. Now, without further ado, let's welcome Dr. Yu Chaoming. Chaoming, please take over the screen whenever you are ready.
Yeah, thank you, Zhengxia, for your introduction. Hello, everyone. Firstly, I would like to thank the Department of Civil and Environmental Engineering at NUS, and also the IES and STRAC-E Joint Committee for organizing this brown bag section. So today I will talk about structural engineers' responsibilities and what we can do in achieving net zero. So I will do a quick introduction about myself. I'm a chartered structural engineer with 15 years of international consultancy experience. I worked on many unconventional structures, like long span structures with complex form and the tall buildings across many sectors. Here are some selected project images. I'm now leading the structures team at Kando, Singapore, and working on some interesting and challenging projects in Asia. About Kando, Kando is a multidisciplinary consultancy, and we have 21 offices globally and 8 offices in APAC region. We became One Planet company in 2012 and the first carbon neutral consultancy in 2020. Kando recently launched a Zero Carbon Design 2030 initiative. We target to design all our projects to be zero carbon by 2030. So here are some of our net zero carbon experience around the world. So why design for net zero? We are all aware that we are living in a climate emergency caused by the increased carbon emission. There are extreme weathers, typhoon, flooding, iceberg melting, and extinctions of organism air pollutions. So if we don't take any actions and keep increasing the carbon emission, it will cause catastrophic results very soon. As an industry, the building and construction sector is responsible for 38% of global carbon emissions. This is based on the last year's data, and we consumed a staggering 40% of the world's natural resources. So all this have a major impact on our planet. So we must make a change to reduce the carbon emission. The World Green Building Council initiated this Advancing Net Zero program to promote working towards decarbonization by 2050 in order to limit the global warming less than 1.5 degrees Celsius. So here are the targets. By 2030, all the new buildings operate at net zero carbon and reduce at least 40% of embodied carbon. By 2050, all buildings to be net zero in whole life carbon. And many countries and organizations have committed to net zero carbon. This is an overview of global net zero announcements. And Singapore is aiming to reach the peak emission by 2030, then halve the emission by 2050, and to achieve net zero in the second half of the century. And to advance the national agenda on sustainable development, Singapore has announced the Green Plan 2030 earlier this year. It covers a lot of aspects, and it's a live plan which will evolve over time. So it covers the building sector as well for both operational and embodied carbon. And in the new recently released Singapore Green Mark 2021 document, basically aims to raise the built environment sustainability standards and encourage to conduct whole life carbon assessment on both new and existing buildings. So you may ask, what is the net zero carbon building? The definition is one, the amount of carbon emissions associated with a building's embodied and operational impacts over the life of the building, including its disposal as zero or negative. So we understand the total carbon footprint for the buildings is composed of embodied carbon and operational carbon. And we need to look at the whole life cycle to ensure the carbon emission of the building is being zero. So in order to do that, we need to decrease both embodied and operational carbon as much as possible. As you can see on the graph, over time, we can reduce considerably the operational carbon, especially by optimizing energy efficiency and stepping away from fossil fuels. Concerning embodied carbon, the reduction is not as effective, mainly because of chemical process involved in the material production. So embodied carbon will take up the majority of carbon footprint of a building. This is Kondo's 7-step strategy in achieving the net zero carbon. So it's from passive design optimization, reduce operational energy demand and consumption, eliminate fossil fuels like coal, gas, oil, and provide on-site renewable energy and storage where possible. We should maximize using the renewable energy like solar panels and the wind energy, etc. And limits the upfront embodied carbon. Consider whole life carbon in conjunction with whole life costing, and publicly disclose performance annually using the RAP database. So for structural engineer, our focus would be limiting the upfront embodied carbon. So what is the embodied carbon? The embodied carbon is the carbon footprint of a material. It's the total greenhouse gas emissions generated throughout the life cycle of the material. This chart shows the building whole life cycle stages, including the upfront, which is from A1 to A5, including the material extraction, manufacturing, transportation, and installation. And for the in-use stage, which is from B1 to B7, it covers maintenance, repair, replacement, and operational energy and water. And end of life would be deconstruction, transport, waste, processing, and disposal. For stage D, the reuse, recycle, and recover is beyond the building life cycle. As you can see, except the B6 and B7 are the operational carbon, all the rest are the embodied carbon. Here I give an example. It's actually from the extra key guide. It's an indicative distribution of A1 to C4 emissions for an ultra low energy residential model. The operational carbon is only taking 23%, but the upfront embodied carbon take taking as much as 55% of total carbon footprint. So this part shall be our focus to reduce. Also, this is the minimum scope for a structural embodied carbon assessment. In terms of the proportion of the embodied carbon directly attributable to the structure, it is in a range of 50 to 85%. As you can see, the structural embodied carbon would contribute to the most of carbon footprint of a building. It is our responsibility to manage and reduce this part of carbon emission. Then how to calculate embodied carbon? Basically, it's the material quantity times the carbon factor for the life cycle modules. Extract published a guide. It's called How to Calculate Embodied Carbon last year. It's very informative and useful for understanding the methodology. I recommend everyone to have a read if you are interested. And there are also other guidance and database you may refer to, like the recast whole life carbon assessment for the built environment, and the ICE, the Inventory of Carbon and Energy database, is a commonly used database, and it provides the carbon factor for stage A1 to A3. In the Asia Pacific embodied carbon primer, some available assessment tools around the world are also listed for reference. Some of these tools will cover the whole life carbon assessment, and some of them only focused on the upfront embodied carbon. And here I selected some tools. One is the Extract-E's the structural carbon tool. It covers the whole life cycle carbon assessment. And another one is the Hong Kong CSE carbon assessment tool. Is an online assessment tool. And the Condo assisted Construction Industry Council in the development of this tool. And they are both free to use, so you can give it a try to help you to understand the embodied carbon assessment. In Singapore, according to the Green Mark 2021 document, we can use either BCA carbon calculator or ICE recast database. The current BCA carbon calculator has a limited database. As you can see, for the steelwork, we only have two options, primary steel and recycled steel. So it wouldn't be very accurate to use the data for assessing the embodied carbon on the project. But I believe this will be further developed to include more materials. And so in the meantime, we can refer to the ICE database. As the carbon factor is geography dependent, before a more developed database becomes available, I would suggest to review the carbon factors used on the project with the supplier to ensure the assessment is more project specific. So besides the commercial tools available in the market, you can also build your own tool using the applicable database. Here it shows our Condo in-house grasshopper-based tool. It can assess the embodied carbon for different options efficiently and to present the results graphically. So it's very straightforward to show which option gives the lowest embodied carbon. We also developed a Revit-based tool via an in-house Dynamo script. It can access, tabulate, and present all the options against the target in one go. So after understanding why and how to do the embodied carbon assessment, we should also have targets to aim for. Here it shows the Extract-E scores targets for A1 to A5 stage. It's a kilogram carbon emission per square meters gross internal area. And the target value here showing on the chart is a solid line, will decrease over time. This target is set to limit global warming to 1.5 degrees Celsius. But we should push ourselves to set a lower value, not higher than the average targets in the chart above. So basically by 2030, according to this, we should achieve the embodied carbon for A1 to A5 to be around 140 kilogram embodied carbon per square meters. So which is type A. Then how can we reduce embodied carbon to meet this target? This is a joint effort by all the parties, from the government to the investor and developers, designers, manufacturers, and researchers. So we as the designers shall educate clients and to let them understand the impact of embodied carbon and specify the low carbon materials and use the life cycle assessment approach, basically from the beginning of the project to the end. And we should optimize our structural design and seek innovative solutions. So for the big picture, we shall design for the circular economy rather than the linear economy. So the linear economy is to design, build, demolish, and dispose. But the circular economy is refurbish, reuse, reduce, and recycle. So we should conserve the resources to minimize the quantity of the structural material used and specify and source the materials responsibly and sustainably. And we should design to eliminate the waste and ease of maintenance. So basically design for reusability and flexibility and manage the waste from the demolition, excavation, and construction. Well, the opportunities for reducing or eliminating embodied carbon will vary between projects. In general, the greatest saving can usually be realized at the earliest stage of a project. So we should include embodied carbon assessment on the agenda from the beginning of the project. This graph shows the carbon reduction potential reduces while the project develops. So basically at the planning stage, we can challenge the brave and propose alternatives. So do we really need to demolish the existing building and build a new one? Can we just reuse the existing building structure? Can we just do some refurbishment, A&A work, basically to reduce the majority of the embodied carbon for building? And during the design stage, we would focus on build clever. So basically make the low carbon solutions, like specify low carbon materials and do the structural optimization. And in the construction stage, you can see the potential of the reduction is the least, because what we can do be only focusing on the construction techniques to reduce the resources consumption, like to utilize the temporary structures in the permanent condition and to maximize the prefabrication to reduce the waste on site. So we know the biggest reduction on the embodied carbon is to reuse and refurbish the existing building. However, more than 90% of the buildings in the world were demolished before end of the serviceable life. So we need to change our industry's mindset to move towards a more sustainable development direction. Here I selected one project example in London. So this is office building, and they refurbished the existing building structure and added a few floors on the top and replaced all the facade with 85% of recycled glass and 100% recycled aluminum, and used 80% recycled steel. So just from reusing the existing structure and saving the construction waste from building a new structure, it saved more than 21,000 tons of carbon emission. So it's really massive. So we should really consider to reuse and refurbish the existing building structures. As the embodied carbon is the carbon footprint of a material, we should specify the low carbon materials on the project in order to reduce the embodied carbon. So concrete is the most popular construction materials, also in Singapore. If we look at its mix, the biggest component is aggregates. So this one is showing the typical concrete C32, and aggregates is taking 79%. But if we look at its embodied carbon, the cement is actually taking 97% of the embodied carbon. So this is because of the most of the carbon emission was generated from its chemical decomposition of limestone. So if we reduce the percentage of the cement in concrete, the embodied carbon will decrease. Currently, the most developed low carbon concrete is the concrete with cement replacement, such as the ground granulated blast furnace slag or the pulverized fuel ash. As you can see in the chart, so the embodied carbon with 80% of GGBS cement replacement is more than 60% lower than the Portland cement. There are also other types of low carbon concrete being developed, such as the carbon cure concrete. It has carbon dioxide injected and mineralized during the concrete production. So the carbon dioxide will be captured within the concrete. And the mineralized carbon dioxide will strengthen the concrete as well. And for the steelwork, the conventional basic oxygen furnace makes the steel using the raw material inputs. The electric arc furnace can make steel using scrap steel and renewable energy. With a high recycled content, the embodied carbon of the EAF steelwork is significantly lower than the conventional basic oxygen furnace steelwork. So we should specify high recycled content steelwork on the projects as much as possible to reduce the embodied carbon. And timber is a low negative carbon material. We say it's negative because it captures the carbon dioxide while the tree grows. This is called carbon sequestration. The carbon dioxide is temporarily stored within the timber and will be released at end of life. So normally we will not include the timber sequestration in the total embodied carbon figure when we do the assessment, but just have it listed separately, as it really depends on how the timber will be dealt with at the end of life, whether it's going to be reused or burned or landfilled. This carbon sequestration may be partially or fully released into the environment. Besides this kind of mass timber structure, we can also consider the hybrid timber structure, which gives more flexibility in terms of material use. Like for the tall buildings, we can use the timber floor and timber beams as the floor framing system, then use the other materials for the vertical elements due to the strength efficiency. A stone is also a low carbon material. So as you can see on the diagram, a much higher strength stone has a very low embodied carbon compared to the concrete. Although it's not popular used material in the modern construction due to its constraints, we can still consider to use stone for like a staircase or facade cladding panels. So talking about the facade is also a major part of the building, and its embodied carbon shall be considered in the whole life assessment. This chart shows the embodied carbon for different facade materials and system. The double glazed curtain wall system has the highest embodied carbon. However, that's the most popular used cladding system in the urban environments nowadays. So in order to reduce the embodied carbon, we should consider more lower carbon systems on the projects, like the precast cladding or stone cladding or brick cladding. Another potential in the design stage to reduce the embodied carbon is to do structural optimization. So even without considering the embodied carbon, we should always do the structural optimization, try to propose the most efficient solution for the project. Here is our approach to do the structural optimization. We should optimize the structural design holistically from overall structural stability, performance, deflection, material strength utilization, as well as the embodied carbon reduction of adopted structural materials. And we should build light through the use of lightweight materials like lightweight concrete, timber, steelwork, and also with the reduced spans. So we should just propose the building with the spans satisfy the function use rather than going for super long span without the needs, because that will help to reduce the material quantity and to propose more efficient structure system. And we can also use the high strength materials like high strength steel and high strength concrete. So that will reduce the quantity of material as well, and the efficient structural systems. And we should also design to code, but without overcapacity. So we've got the design safety factor from the code, but some people still prefer to design for a low utilization ratio. But in doing so, you will waste a lot of materials. Basically, it's not really necessary. So we should really maximize the utilization ratio and try to do the structural optimization to propose the efficient structural design. This is the conventional method doing the structural optimization. So it's a step-by-step from topology optimization to the shape, to the sizing, and then the material. And this is how we do it now by implementing computational design to automate the process. So we can build the geometry, loading information, section, and the material properties via the parametric modeling. And we can adjust all these parameters efficiently to find out the most efficient structural design. Here is a snapshot of our in-house script doing the structural optimization. To reduce the embodied carbon, we should also minimize the on-site construction work to reduce the waste and energy used on-site. So prefabrication should be considered and maximized. So when we talk about prefabrication, maybe a lot of people will think of PPVC, but PPVC is suitable for like the residential buildings or hotels, but not applicable to all the other like building types, like for the large open office space or retail, etc. But we can still consider prefabrication because it's not limited to the PPVC. It will be like from the component, like single elements to the modules. So all the steelwork would be prefabricated. So, and also the precast concrete members are prefabricated. And in terms of the module, we can also specify the facade panels and bathroom port to be prefabricated units. And we should also design for deconstruction and recycle to minimize the demolition waste. For the steel structure with the bolted connection can be easily disassembled and recycled, and marked steel members with product information can be reused. Similarly, for the timber structure with the screw fixing can be also easily disassembled at end of life. For concrete, instead of a landfill, concrete can be recycled. The crushed and recycled concrete can be used as a paving material or aggregate substitute for mixing new concrete. So here I'm going to show a case study in which the embodied carbon assessment is integrated with structural optimization exercise. And the project is an office tower in Tokyo. It's Grosvenor's first zero carbon ready building in Japan. And we were appointed by the clients actually after completed the structural design and to look at the possibility of using different materials and what are the influence on the embodied carbon of the project. So here it shows the workflow of this case study. This is only focused on the embodied carbon assessment, but not having the other factors like for the structural optimization, as I said, because that's done after the structural design was complete. So the workflow includes from the model setup to the analysis to the assessment and then the summary. Here is the geometry input. We include the grid line dimensions, the floor height, and the number of the base as the variable parameters, and we can change easily later on if we need to adjust the design. And here are the components for setting up the geometry of the building. These are the components for the loading input. Again, for the loading values that can be variable parameters, and we can define the loading application direction and also the different load cases. And here it comes to the structural analysis and output. We can plot the stresses, the displacement, utilization ratio of the member, or the forces and bending moments. This one is our script for the embodied carbon output. So it covers from A1 to A5. For A1 to A3, which is called cradle to gate, is the data we took from ICE database. And for A4, which is transport, basically it really depends on where are the sections manufactured, and that can be calculated based on the distance of transportation and the weight of the transport. And for the A5 is the waste, how the waste will be, construction waste will be dealt with. Normally, we can just assume a percentage to estimate this part of embodied carbon. Then we look at the analysis results. So here it shows the stresses plot for the one option, and also the displacement and the forces in the members. Here are the 5 different options we studied. The first one is the base scheme, basically is proposed by the structural engineer for the project. It's a precast concrete plank with the structural topping for the slab, and all the primary and steel and the secondary beams are in steel, and the columns are also the steel columns. And here we can plot the charts for based on the different structural elements, and to see which one is actually taking the most of the embodied carbon. And for the option 2, we replaced the RC slab with the cross-laminated timber slab with the concrete topping. The concrete topping is to help on the acoustic performance of the timber floor. And so here we have the embodied carbon results for the different structural elements. And we also list out the timber sequestration as a separate chart to understand the influence. And the option 3 is similar to the option 2, but just replacing the secondary beams to glue-lam timber beam. So we will have more timber sequestration and less embodied carbon. Then option 4 is basically all the floor framing system would be in timber, and the column still in steel. Then option 5 is similar to option 4, just replacing the columns from steel with the RC. So here is the summary in terms of the material quantity for different options and the embodied carbon comparison. As you can see for the option 5, the material quantity is actually quite high because it's not very efficient like for the sections. But for the rest of them, basically it's kind of aligned with the embodied carbon chart. So we use more timber on the project may reduce the embodied carbon, but we still need to look at the structural efficiency. Like for some of the highly loaded members, it's still better to use other kind of structural material like steel or concrete compared to the timber. And here we have the chart for the timber certification table for all 5 options. So now I would summarize on the embodied carbon reduction. So we should consider it early in the design stage because the earlier that's being considered and the bigger reduction can be made. And we should maximize to reuse and refurbish the buildings rather than demolish and reconstruct, and specify the low carbon structural materials like the concrete with cement replacement and steel with high recycled content and timber and also stone. And we should conduct structural optimization on the project during the design stage. In the meantime, to carry out the embodied carbon assessment to determine the prime solution for the project. And we should also consider the prefabrication to reduce the construction waste, and that will help to reduce the construction program and also have higher quality of the products. And we should also design for the deconstruction and the future upcycling. So that's all of my presentation. Any questions would be welcome.
Okay, thank you, Chaoming, for the very informative sharing. And I personally learned a lot about carbon neutralization today, from global perspective to net zero movement in local context. It's a very detailed account of fundamentals on embodied carbon. Once again, on behalf of AES SRE Joint Committee, thank you for taking your time to promote sustainable design and how we as structural engineers play an indispensable part in offsetting carbon emissions. It's meaningful for us to first understand in what way each of us can contribute. I'm sure our campaign against carbon footprint will slowly gain traction. There are some questions in the chat group. Maybe first, let me read out the first question.
Yep.
Yeah, okay, first one is Ziyue asking. Okay, wait. Can you read the question, Dr. Yu? I read about the digital twin city from news where ramifications of carbon reduction measures could be simulated while a virtual model. So specialists can make an informed decision. Is it similar to what you have been working on BIM and Revit model? And do you think it will become a standard virtual design process in future?
Yeah, I definitely agree so. So basically, at least in Condo, we do the embodied carbon assessment on all the projects, even if the client doesn't really request for it, but we will do that to understand the embodied carbon. And like the tools we use either in Revit or in the Grasshopper that will help us to efficiently get the results and for the comparison for the optioneering. Yeah.
Okay, good. Thank you. Okay, next question is I asking you, I know you give us one project example. So can I check you in in your past project, which project is the most memorable you feel actually carbon footprint reduction? Design.
Yeah. Yeah, so we actually recently done one project, but it's confidential, so I cannot give much of the detail. But for that one, we actually explored a lot of different options, different materials, the sustainable materials. And so the project is a tall building, actually, and we try to maximize the use of the sustainable material and to optimize the structural design, like with the more manageable spans and the more efficient structural system. So that's helped to reduce the embodied carbon to quite low value. So that's actually quite challenging for a tall building because there are much higher loading. So in terms of the column and the foundation size, you cannot reduce quite significantly, but we still manage to reduce the embodied carbon. So that will involve using some of the innovative materials. And like what I mentioned for the carbon cure concrete is also available in Singapore with the local supplier. So we should try to use as much as possible that type of materials. Yeah.
Okay, good. Okay, I think everyone I just shared with you my experience in this efficient design. Okay, you know I'm from Warham.
Yeah.
I think 10 years ago when I do this garden by the bay, the steel roof. Initial before we Warham take over the main project, actually the client already MPAS already awarded the steel specialist. So the steel specialist is from Hong Kong. They engage one designer. So they do the steel roof design. The total tonnage of steel roof about 6,000 tons at that time. So the design assumption, they are using the support is fixed support. When we took over the project, coordinate with them, first we are seeing how come the steel structure is so heavy. Then we engage Professor Richard Liu from the US. We have many discussions among the consultants. Then we feel actually the assumption in terms of connection and the loading distribution, plus the construction sequence is very important. After we do the detailed analysis, our final, the steel tonnage reduced to 3,600 tons. I feel this carbon definitely is really at that time, 10 years ago, we not talk about this carbon reduction at that time, but for me, this is a good project. As an engineer, we need to provide the efficient design. Don't over design.
Yeah, totally agree. Yeah, so yeah, we all love the elegant and efficient structure. Yeah, instead of very bulky, especially for this kind of the architectural steel design.
Yeah. Okay, good. I think another one from our committee member, Steve, also asking you a question. First, have you done any study to use where the passing score of the BC carbon calculation sits on the SRE score?
I'm not sure. Are you actually referring to the new Green Mark 2021 document? So there it gives some targets. I'm not sure if you are referring to that one. Or
the target, so basically just want to see which one is more stringent.
Is the SRE score one. So for the Green Mark document, it's actually, in my opinion, it's quite high. So we should really try to push ourselves to reduce like at least more than half from that target. So the SRE one, if you look at that for the type A building, is only 140 kilogram carbon emission per square meters. So it's quite the number is quite low compared to the Green Mark document.
Okay, next question by Steve. Do you know of any software, be it structure analysis or BIM software, which can calculate the embodied carbon based on users' input?
I'm not aware, like for the commercial structural analysis software, I have this embodied carbon built in. Maybe there are, but I'm just not aware of that. Because for us, we're doing that, we have our own script to extract the results and plot the embodied carbon data.
Yeah, Steve, for
Yeah.
this one, Warham recently, we also tendered a number of projects. At the moment, we also don't have any software. We are using actually in-house spreadsheet to do the calculation.
Okay, all right, thank you.
Okay, I think next one is from John. Dr. Yu, I wonder what the score is of a combined floor system.
I'm not really sure what's this kind of floor system, sorry. So would you please explain it?
Yeah, this is John, is it? Is it John Newton? Okay, maybe, okay, his next question regarding of reuse of existing structure, I always like to use the word donor skeleton. Okay, actually the reused material for Singapore, we are using recycle aggregate. Certain steel structure we also can be reused also.
Yeah, and also for the buildings, like for the existing building structure, we should try to maximize to reuse and refurbish. Because I know a lot of like buildings only like 20 or 30 years old here, and they are demolished and build something new. So this is really the one we should look at and try to change our mindset to do the refurbishment. So as you can see, if you do some like refurbishment on the existing structure, it's still like giving you the aesthetic view and also satisfy the better function use. Yeah.
Yeah, for this combined floor system, I guess it's a Bible deck system. I guess it's that. You know, I think Singapore have this one for Warham project. We also have done residential project by using this type of floor system. Of course, for this system, actually the concrete usage is reduced. Also, we can achieve our design requirement, you know, the user requirement.
So which kind of
the structure system is a bubble deck system inside the actually a concrete slab or concrete
I know.
Bubble.
Yeah, I think the different country has a different name for that type of. Yeah, I've used that in the past on the project actually. So that will increase the floor span, and the slab itself is much lighter, so you can omit basically secondary beams, and that's a big saving on the structural material as well. Yeah.
Okay, next question is from Harry Canhill. In your professional opinion, do you believe that the net zero targets by 2050 are realistic with current construction techniques, material, practice? Or do you think that the further innovation is required to reach net zero?
Yeah, so with the current techniques, I think we really try to achieve net zero without carbon offsetting. It's not possible. So that's why it's quite important for the researchers to develop the new structural materials to reduce the embodied carbon. But I think we are seeing a lot of this kind of recent innovative materials being developed. So I believe that target can be achieved by 2050 because we still have nearly 30 years to get there. But for now, to design the net zero carbon building, so it will always involve some of the carbon offsetting in order to achieve the net zero.
Yeah, actually it's a long way, but we engineers or all these student members, I think you all can contribute more.
Yeah.
Yeah. Thanks, Chaoming. I think now is 1:26. Left 4 minutes. Maybe I give a closing remark. I believe many of the participants who joined us today are the student members. As we approach the end of the year, let me just do a quick roundup. We have tried our best to procure a list of virtual events for our young members. I hope you all enjoy all of them. And please continue to send us your feedback to help us to improve. During the journey, NUS Norilla has been a big help to us. On behalf of AES SRE Joint Committee, we would like to convey our appreciation for the quality work provided in facilitating an areas of virtual events that we have jointly organized with NUSCE department. We are truly grateful to Norilla for the hard work dedicated to making the events professional and hassle-free. Those online talks and seminars have played a crucial role in connecting us amid the COVID-19 pandemic, where physical interactions are restricted. And they would not have been so successful without your help. Thank you, Norilla. Norilla, you're muted. And also,
yeah, welcome.
Yeah, thank you. Thank you, Norilla, on behalf of again. Ladies and gentlemen, I hope you all enjoy the events organized by us so far. We are looking forward to organize more in the near future. Hope can see you all soon physically. Stay safe and healthy. Thank you.
Thank you.